back in the SSD office, but you might need to take some actions in that space. Some practice problems for said midterm. I did send out an email saying something to that effect, right? Okay. Let's go into the back. While that gets passed out, maybe I'll use this to motivate like what stuff's gonna happen in the next couple days. So let's just take a look at these topics. In order to like do well on this exam, you should be able to do some inverse trigonometry, know the philosophy of what inverse sine, inverse cosine mean. You should be able to use them to solve some trig equations. Simple trig equations like those, or more complicated ones where you have to do some algebra. There's a fair amount of problems that just have you identify like what the solutions should look like. You should be able to use the area formula, law of sines, and law of cosines. The actual exam isn't going to be 35 questions long. So be able to do that. All right, like if you know this information and you know the area, can you use the area formula and the other facts you know to figure out what the side length C is? Cool. Do things like figure out the lengths in this diagram using the philosophy we have of like these triangle rules. The only thing in here which is not yet reflected in stuff we've covered, it goes forward, not backward. I did it the counterintuitive way. Is the angle addition formulas. What happens to trig functions when you add together angles? What happens when you do cosine of a plus b? Is there some sort of nice formula for that? Because one thing it's definitely not is it's not cosine a plus cosine b. That's like obviously wrong, because then you would wind up saying like cosine of 0 plus 0 should be cosine of 0 plus cosine of 0, which is 2, and that's not equal to 1. So that can't be right. So let's start it on angle addition. And, oh yeah, trig identities will be appearing on the exam too, so, what's the main point that I'm going to have with trying to prove trig identities? Make sure you explain all the steps. If you have like perfect work on the exam, but you haven't written down any words, you'll probably get about 50% on that problem. So, cool. Any questions about that sort of stuff? Same rules as usual apply on this exam. You'll be allowed a note sheet that you'll write yourself. You'll turn that note sheet in at the end of the exam and you will never see it again. If you want to get a copy of your note sheet back, make 2 copies of your note sheet before you start. Which probably you should do anyway, because that it's like studying, right? Cool. Let's do stuff. Maybe before I even begin that, people have any questions they want to address before we start it? All right. So, as usual, I usually expect some portion of the class to have already seen basically any topic that I mentioned. How many people have seen the angle addition formulas at some point? How many people remember the statement of the angle addition formulas? Oh, good. So let's state them. And as with some of the stuff that we've done recently, like law of sines, I'm not going to try to prove the angle addition formulas to you. We'll write them down, see how to use them, then there will be some challenge problems in which you'll prove the things. So what do the angle addition formulas say? They say that the cosine of a sum of 2 angles is given by the product of the cosines of the angles minus the product of the sines. It says that if you want to take the sine of a sum of 2 angles, we'll take the sine of the first times the cosine of the second, and add to that the same product but with the sine and cosine swapped. Now that those are like written down, what do you think? Do those look familiar, I hope, to the people who said you'd already seen them? That's good. These are formulas that are worth knowing. They're important for like trying to do new computations. And they let you like solve equations that you couldn't before. So you'll notice I have a formula for addition and a formula for subtraction. I bet if we just know what happens for addition, we can figure out what happens for subtraction. And let's even demo doing that because, well, right, it's really easy to accidentally forget a formula. And it's nice to be able to like verify it using other things you know. So let's try to figure out what should the cosine of A minus B mean. Oops, I'm off screen. Well, what is subtraction in terms of addition? That's like the same as plus negative B? Let's use that. Oh, cool. I have a formula that does addition for me. That's the cosine of A times the cosine of, I'm going to emphasize the negative sign because we're going to do something with it, negative B minus sine of A sine of negative B. And now what can I do with those negative signs? What does a negative inside of a cosine do? Well, what can I do with that negative sign? I can just get rid of it, right? Cosine is even. Don't care about that. What can I do with that negative sign? Move it up front. So I could pull it in front of that sign, then you'd see negative sign times negative sign. Well, I could just put the negative sign in front of the whole thing and the negative signs cancel. Cosine of A minus B is cosine A cosine B plus sine A sine B. And I'll put it on the board. Cosine of A plus or minus B is cosine A cosine B minus plus to indicate that it's like plus or minus, but in the opposite case. Sine A sine B. And let's just try to think through what should happen for sine. I'll use the fact that I have colored pens and then we'll erase and move negative signs as appropriate. So I should wind up with sine A cosine negative B plus cosine A sine negative B. All right, and now same game. Do what you should do with those negative signs to simplify. What do you get?
Sine A cosine B minus cosine A sine B.
Nice. That negative is inside of a cosine. Cosine is even, so it doesn't matter. Don't need to put a plus sign there, it's just cosine B. Cosine A is just cosine A. Sine B is the same as negative sine B, so I can pull that negative up front. Feel pretty good? Nice. Groovy. And I have space on the board for tangent. We'll get to that by the end of today. So what's the most obvious application of these things? You know what? I haven't proved it, but let's actually do something to try to check these formulas. Like, the most convincing thing other than a proper proof that we can do is like look at some graphs. So let's do that. Let's like graph sine of A plus B. We'll graph whatever's on the other side. We'll see what happens. But the graphs I'd like to look at only have one free variable. So I'll just set A to be a constant, and I'll just do cosine of x plus A. So let's do that. That QR code should go to this graph. So let's see. There's the cosine of a sum. There's what the angle addition formula says it should be the same as, I hope. Hopefully those look the same. And to check it's not a mistake of the choice of A, those look right? Cool. And that is definitely not a graph one should continue to have up and moving while talking. Same thing with sine. Looks like the graph of sine, but like shifted by however big this b is. There's the angle addition formula. Yeah, cool. And won't write it down yet, but there's what happens when you shift tangent. Seem good? All right. So, these formulas look right, but why are they useful? One of their main uses is they let you do new computations that you couldn't do before. 5 pi over 12, that's not an angle on your unit circle, right? Oh, but is it a sum or difference of angles that you do see on your unit circle? And this isn't something that should be like obvious off the bat that it is, but give me two angles on your unit circle that when you like add or subtract them, you'll at least get a common denominator of 12. Cool. Let's try it. Add those two things together. Let's see if we get 5 pi over 12 as a result. We'll definitely get something divided by 12. So get a common denominator, add those together, tell me what you get. I hope it's not 5 pi over 12 because like, I want to like demo this as like a guess and check and revise your guess strategy. What you get? It's definitely something pi over 12. I hear a 7. Cool. How many people have even totally forgotten how you're supposed to add fractions and want me to do that? Okay. Alright, so you need a common denominator. So let's do that. So you multiply this by 4 over 4 to get that 4 times 3 in the denominator. Multiply this one by 3 over 3. 4 times 3 is 12, 3 times 4 is 12. So you have a common denominator, so it's easy to add fractions. 4 pi plus 3 pi, yeah, that's 7 pi. Which importantly is not 5 pi. So this would be great if I wanted to compute trig functions at 7 pi over 12. Give me another guess. Give me another two candidates that might result in a 12 in the denominator. And I guess I want one of them to be a little bit smaller.
Over 2 and pi over 6.
I hear a pi over 2 and a pi over 6. Let's try it. Cool. So what's the common denominator? 12, but there's like a simpler common denominator, right? Because what's the least common multiple of 6 and 2? Yeah, so you just multiply this by 3 over 3, we're going to end up with, gosh, I guess 4 pi over 6. 3 plus 1 is 4. That's actually just 2 pi over 3. That was already an angle we knew. Yeah. Pi over 4 plus pi over 6. Least common multiple between those two is definitely 12. That's good. And pi over 6 is a little bit less than pi over 3. So there's hope. Add those fractions. Do you get 5 pi over 12? Oh, nice. Anyone come about it and get like a different pair of things you could add or subtract to get that? There is one. There's a way to subtract, but that doesn't matter. All right, let's do it. So let's see. 5 pi over 12 is apparently pi over 4 plus pi over 6. Those are both angles whose trig functions you know. Let's use the angle addition formulas to compute some trig functions. I think the way that I want to do it is let's do the one for cosine altogether, and then I'll be quiet for a bit. You'll tell me what happens with sine. All right, so this thing should be the same as cosine of pi over 4. Now let's write out what it is and then use the formula. Plus pi over 6. Well, that is cosine A, cosine B. So multiply together the two cosines. Equals cosine of pi over 4, cosine of pi over 6, minus, because cosine angle addition gives you a minus, sine pi over 4, sine pi over 6. And those are all angles that appear on the unit circle. So let's use that. Cosine of pi over 4 is take out your unit circle if you need to.
Root 2 over 2.
I hear root 2 over 2. Cosine pi over 6 is
Root 3 over 2.
I hear root 3 over 2, but there was a question mark at the end. Do I hear a second? Awesome. Minus sine of pi over 4.
Root 2 over 2.
Sine of pi over 6.
1/2.
And in some sense, there is an answer. There's no more like trigonometry involved there, but let's simplify a little bit. What's the common denominator between all that?
2.
Well, 4, right? Because that's multiplication. Right, 2 times 2 is 4, 2 times 2 is 4, so the common denominator is 4. Root 2 times root 3 is root 6. Right, square root behaves well under multiplication. Minus root 2 all over 4. Groovy. Feel pretty okay? And I guess we could double check that now using a calculator to get some decimal approximations. But instead, you know what? Do the next line. What's the sine of 5 pi over 12? Once you have an answer, once you come down to an answer, go ahead and check it by comparing with those around you. See if your walk and your final answer agrees. Those of you who have calculators, you can also just straight up just ask the calculator, what's the sine of 5 pi over 12? It'll give you like a decimal approximation. Also compute the decimal approximation of like the answer you get. Cool. What are we getting?
Square root of 6 plus square root of 2 over 4.
Cool. Do I hear a second? Nice. Do I hear a call to go through the walk? Cool. Then let's do it. So, I want to compute the sine of 5 pi over 12. The starting point of this whole thing was 5 pi over 12. I can write that as a sum of two angles that I do understand. So this is the same thing as the sine of, let's do more color coding. Pi over 4 plus pi over 6. And now that we've done that, we have an angle addition formula. Angle addition formula for sine says I should do sine times cosine plus cosine times sine. So let's do that. So I should see sine pi over 4 cosine pi over 6 minus sine, nope, cosine times sine. Cosine pi over 4 sine pi over 6. I copied those things down correctly? Awesome. So now, all of these things are things that you see on the unit circle. So let's use that. What's the sine of pi over 4?
Square root of 2 over 2.
Cool. So I should see a root 2 over 2. Cosine of pi over 6.
Square root of 3 over 2.
Square root 3 over 2. Minus cosine pi over 4.
That should be plus sine.
Oh yeah, it should. Thank you. See, I got so distracted by like making sure to switch colors correctly that I, screwed up the more important thing. Cosine pi over 4.
Root over 2.
Sine of pi over 6. Nice. And now let's just make sure that things have happened correctly. 2 times 3 is 6, but there's a square root around it. That denominator is 2 times 2 is 4, 2 times 2 is 4, so the common denominator is 4, big denominator is 4. Root 2 times 1 is root 2. Cool. Nice. So there's one use of the angle addition formulas. You can now compute trig functions at more angles. In fact, here's a nice exercise to do. Start with the unit circle you have. What are all of the angles that you can now do? I'm not going to spoil the answer. It's slightly unsatisfying because it's not that many new angles. But work it out. See what you can do. Next thing I want to do, well, yeah, let's do this. We already have a formula for what happens when you do pi minus inside of a sine or a cosine, right? Just by remembering, what's the sine of pi over 2 minus x?
Cosine.
Yeah. Because pi over 2 minus x just swaps the sine and the cosine. Let's double check that real quick. So what should this be? Well, I see subtraction. So that should be sine pi over 2 cosine x. There's a minus, so minus cosine pi over 2 sine x. And that's just, now work it out. What's the sine of pi over 2?
1.
1. That's one of the things that you shouldn't even need to look at the unit circle, right? It's a right angle. So 1 times cosine of x is cosine x. Cosine pi over 2.
0.
Minus 0 times sine x. Cool, that's a 0. Yeah, it all covers it correctly. So that's kind of nice. In fact, if you find yourself in a situation where you've forgotten the angle addition formulas, do you think you could do something like that to check if your formula you're trying to come up with is right? Because you know what each of those look like. It's just multiply together 2 trig functions and then add or subtract the other 2 trig functions. If you do it wrong, doing a checksum like this will tell you. All right, so here's another thing that you can do. So you know how we did lots of examples previously where it's let's suppose I give you an angle, its cosine is this, and it's in this quadrant. Can you compute all of the trig functions? That seems like it pairs with angle addition pretty well. Let's try to do that. Suppose I give you an angle A and an angle B. I tell you cosine is A is 3/5. Cosine of B is 5/14. A is in between 0 and pi over 2. B is in between 3 pi over 2 and 2 pi. What's the cosine of A plus B? So let's start by just off in this space right here. I know the first step it says is to compute sine of A, but let's see why we want to do that. What's the angle addition formula for cosine say this should be the same as?
Cosine A times cosine B minus sine A times sine B.
And in fact, it might even be useful. I know it's written down now, and you just told me what it was. But I think it would be useful for everyone to say that, just to reinforce it in memory. Tell me, what's the angle addition formula for cosine? Cosine of A plus B is?
Sine A times cosine B minus sine A times sine B.
You harmonize very nicely. All right, so let's use that. In this problem, do we already know what cosine of A is? What is it? 3/5. Cosine of A is 3/5. Do I already know what cosine of B is? What is it?
5/15.
Do I already know what sine of A is? No, maybe you do already because you're like walking ahead, but I don't yet. Do I already know what sine of B is? Cool, I guess we better start by figuring out those. How do you figure out sine of A if you know cosine of A? Pythagorean identity. And then you also need to worry about like what quadrant it's in. So, well, we're about to do cosine, sine of B on the next page. So let's do sine of A together. So, A is in between 0 and pi over 2. So what quadrant is that in? Yeah, quadrant 1. So I expect sine of A to be positive. So let's use that. So cosine A is 3/5. I would like to know sine of A. So let's draw this. So there's the angle A. I know cosine of A is 3/5. If I'm going to use a right triangle to do this, what sides of this triangle should I label? Hypotenuse and adjacent. What should I label them as?
Hypotenuse is 5, adjacent is 3.
Nice, because cosine is adjacent over hypotenuse. Oh, nice. So what's the other side? How many people did that by actually doing the algebra? How many people did it by just remembering there's a Pythagorean triple? Yeah, nice. They're handy to remember. Oh, cool. So what's the sine of A?
4/5.
Oh, nice. Sine of A is 4/5. So, the next step, I guess, appears on the next page, which is somewhat awkward. Let's re-summarize everything at the top of the page, because otherwise, flipping back and forth is annoying. I know cosine of A is 3/5. I know sine of A is 4/5. I know cosine of B is 5/13, and I know 3 pi over 2 is less than B is less than 2 pi. Ah, that wasn't on page screen at all. Alright, so next thing we need to figure out is sine of B. That's easy enough though, right? Cool. Find for me sine of B. Maybe you actually have to do the algebra to figure out that missing side length, but it is also a Pythagorean triple, so I'll give you this for free. You should get some whole numbers appearing. sine of b computed. Compare with those around you. Cool. Folks feeling confident? All right. Let's hear it. What is the sine of b?
12 over 13.
I hear 12 over 13. Do I hear a second for 12 over 13? Do I hear an anti-second for 12 over 13?
Just negative 12 over 15.
I hear a negative 12 over 13. Do I hear a second for negative 12 over 13? Oh, cool. Let's decide between positive or negative. Convince me. Why should it be positive or why should it be negative?
It's in the fourth quadrant, so the sine value is negative.
Cool. That's quadrant 4. So sine of b should be negative. So what's like the big lesson here? Like this is just a reminder of things from before. Whenever you use like right triangle stuff to figure out trig functions, you might be lied to because the right triangle picture will always draw out like it's in quadrant 1. So you have to think about what quadrant it's in separately. Cool. But in the meantime, I've forgotten everything that you just said. What was the sine of b?
Negative 12 over 13.
Nice. Is there a call to go through the walk? Cool, let's do it. So, I want to compute sine of b. Well, sine of b by SOHCAHTOA is going to be the opposite over the hypotenuse in a right triangle. And what fact do I know about the angle b? I know cosine. So let's use that. Cosine of b is 5 over 13. That's the adjacent over the hypotenuse. And like there's one of two things you can do now. You can just straight up draw the picture and like worry about quadrants later. Or you can worry about what quadrant it's in right now. Since I've already said it, I'll worry about what quadrant it's in right now. So this thing needs to be drawn like it's in quadrant 4. So there's a little like coordinate axis to tell me that there are quadrants going on. There's the angle A. So there's our right triangle. What sides can I label?
The opposite of the hypotenuse. Or the adjacent hypotenuse.
That's better. Yeah. And the opposite side I need to figure out. And like one of two things could have happened. You could have just said, well, I remember this Pythagorean triple, or I can do the algebra. And people just remember the relevant Pythagorean triple. Cool. I didn't expect it to be many. Good on you if you did. Let's figure out this missing side length by actually doing the algebra. So, side squared plus side squared equals hypotenuse squared. So, 5 squared plus the opposite side squared should be equal to 13 squared. Fair enough. And now I guess, like, you have to do the algebra. I guess one place to start is by doing the computations. What's 13 squared?
169.
169. And let's subtract 5 squared to the other side. What's 5 squared?
25.
That should be equal to opposite squared. So it looks like I just need to take the square root. But let's also like simplify the right-hand side. What's 169 minus 25?
144.
144. So the opposite is going to be the square root of 144. But like, I don't know, depending on the philosophy you're taking, either it should be negative because it's pointing down. It's in quadrant 4. Or like, who cares, I'll just remember that it's going to be negative at the last step. So I'll put the negative sign here. Maybe that's good enough. All right. And in some sense, like that's a big number. I don't necessarily always expect people to like be able to simplify square roots of big numbers, but you also had a calculator. So what's the square root of 144? 12. So I'll wind up with negative 12. So sine of b is opposite. Nope. Yeah. opposite over hypotenuse is negative 12 over 13. Cool. Feel pretty good? All right, now let's put things together. Let's do the angle addition. So I now know cosine A, sine A, cosine B, and sine B. Let's put those all together to do angle addition. Cosine of A plus B, let's walk that out. And sine of A plus B, we'll need to do that too. All right, two options. I can be quiet for a bit. You can look at the board and write down the formula and do the walk on your own. Or I can talk through one of them and then let you do the other two. People want me to talk through one of them, one or the other? Cool. I'm going to be quiet for a bit. You are going to compute these two things. Hopefully the angle addition formulas are also on the board. Cool. Let's talk through. So we have an angle addition formula for cosine. So let's use that. We'll end up with cosine A, cosine B minus sine A, sine B. So we'll talk through this all together. Those of you who want to like walk ahead, do the thing for sine, and then we'll like see what people have settled on. So let's just put things together that we already have. What's the cosine of A?
3/5.
3/5. What's the cosine of B?
5/13.
5/13. Minus, what's the sine of A?
4/5.
4/5. What's the sine of B?
-12/13.
And let's emphasize that negative sign to make sure I don't lose it. Cool. So this is what we get if we plug in those values. In some sense, there's an answer. Now it's just a matter of simplifying. This is a rational number, so let's express it as like number divided by number. And maybe a good fourth step is that. All right. So you might look at that and say, well, the 5 and the 5 should cancel, but I think that's not actually useful here because eventually I'm going to like need a common denominator. So let's just multiply across. So 3 times 5 is 15. What's 5 times 13? 65. Maybe you used a calculator to do it. No shame if you did. Plus, the same thing over here. 4 times 12.
40.
Denominator.
65.
65. So between these two fractions, what's the common denominator?
65.
Oh, cool. So it's just easy to add fractions. 15 plus 48.
63.
Cool. So there, we've computed cosine of A plus B. How many people in the time that I was doing that just did the computation for sine of a plus b? What'd you get?
Negative 16 over 65.
I hear a negative 16 over 65. Do I hear a second? Do I hear a call to do the walk for sine? Cool, let's do it. Sine of a plus b is going to be sine a cosine b plus cosine a sine b. And now we'll do the same walk. Given the stuff that we've already done, what's the sine of a? 4/5 times, what's the cosine of b? 5/13 plus, what's the cosine of a? 3/5. What's the sine of b?
Negative 12/13.
Cool. So we have this. Now it's just a matter of doing the same sort of walk again. And I'll propose the same initial step. That's the same as subtracting fractions. Do these already have a common denominator? What's the denominator? 65, because 5 times 13 is 65, 5 times 13 is 65. So denominator is going to be easy. Numerator, 4 times 5. 20. Minus 3 times 12.
36.
Oh, cool. When you subtract those, do you get negative 16? Groovy. All right. So here's one last observation I want to make. So let's take those two facts together. By looking at those two facts, if you want to draw the angle A plus B, what quadrant are you in? Cosine positive, sine is negative. What quadrant? Cool. So it's going to be down here in quadrant 4. And we can draw a right triangle of this. That's adjacent over hypotenuse, opposite over hypotenuse. Oh, cool. All those are like whole numbers? And that's a right triangle. I guess that means 63 squared plus 16 squared is equal to 65 squared. There's a new Pythagorean triple. Think you can construct like infinitely many Pythagorean triples by iterating this? Yeah, cool. Not all of them, but you can get a bunch of them. Cool. I feel pretty good. It's also not the most efficient way to construct Pythagorean triples, but it's nice to see connections. All right, 7 minutes on the clock. I'm going to jump around a little bit in order to make sure to hit things in an order that they make sense between today and Wednesday. I'm going to write down the angle addition formulas for tangent, then we'll use it. If you want to add together two angles, tangent of A plus B, the formula you'll get is tangent A plus tangent B. So you'll just add the tangents together, so that's obviously not enough. And then you'll divide by 1 minus the product. And if you subtract, you'll subtract the tangents all over 1 plus the product. And that's, maybe a less frequently used formula than angle addition for sine and cosine. I guess one thing that's nice is it only involves tangent. To use angle addition for sine and cosine, you need to know both sine and cosine. If you want to use angle addition for tangent, you just need to know tangent. Let's use that for something. Let's compute the tangent of 7 pi over 12. And I guess we have the same starting point. Find me a pair of angles that you do understand which add together to 7 pi over 12. And I guess depending on how much you wrote when we were doing it the first time, I think we did get that out of one of them. Cool. What two angles add together to 7 pi over 12?
Pi over 3 and pi over 4.
I hear a pi over 3 and a pi over 4. Cool. So this should be the same thing as the tangent of pi over 3 plus pi over 4. Oh, cool. Now we can just use the angle addition formula. This is tangent pi over 3 plus tangent pi over 4 all over 1 minus tangent pi over 3 tangent pi over 4. And now let's just carry on. Using your unit circle, if you need, what's the tangent of pi over 3? Right, even the folks who have internalized stuff for sine and cosine, maybe you need to check for tangent.
Square root of 3.
Are you a root 3? Right, like it's either a root 3 or root 3 over 3. And I think it is root 3. What's the tangent of pi over 4? This one you should have memorized. It's like a nice number, it's 1. All over 1 minus root 3 times 1. Oh, cool. That's like a fairly satisfying answer. I guess if you want to simplify it some, you don't like the square root in the denominator, so you could do just like when you add, like, divide complexes by each other. But that's not important right now. That feel pretty good? Nice. All right. One additional formula that will be relevant because we'll use it to figure out. Right, so just angle addition can get you like a few more entries in the unit circle, but like only finitely many. There will be another thing that we'll do next time, which will be the half angle formula. What happens when you divide an angle by 2? We went to that today, but the basis for it will be understanding what happens when you multiply an angle by 2, because then you can just like undo that formula to get a half angle formula. So let's try to do that. Let's get a double angle formula. Cosine of a double angle, well, that's the same as cosine of angle plus angle. Oh, cool. We have a formula for that. This should be the same thing as cosine theta plus or minus sine theta sine theta. Oh, cool. Does that simplify? Yeah, what's cosine times cosine? Cool. There is one of the 3 double angle formulas for cosine. There are 2 others. And let's think about like the motivation for why there should be. That involves a sine and a cosine, right? Does it need to? Why not? I could use the Pythagorean identity. I could either get rid of the cosine squared or I could get rid of the sine squared. I guess the 2 will give me 2 different things. Maybe it makes sense for us to get rid of the sine squared because then I have cosine in terms of cosine. So let's do that. What can I replace that sine squared by?
Minus cosine squared.
Cool, let's do that then. So if I do that, this should be the same thing as, I'll leave the cosine squared alone, minus, big parentheses, 1 minus cosine squared theta. And now I guess we need to stare at that for a few seconds and simplify it. Right, those parentheses are like pretty important, right? Otherwise you'd probably wind up with like -1 or something incorrect. So I guess let's distribute the negative sign through it. That's -1 plus cosine squared theta. So what's that simplify to?
2 cosine squared theta minus 1.
Oh, cool. So there's another double angle formula. Maybe this one looks more usable because in order to use it, I only need to know cosine of theta. Nice. And, well, you know what? Maybe I'll even give you some like stuff to do and be able to answer when we start next time. Get another double angle formula for cosine that only uses sine. Figure out the double angle formula for sine by doing the exact same trigger. There's only going to be one formula. And then by demand, if people like, we'll go through the walk to derive where the angle addition formula for tangent comes from. So at this point, you should be backing up. I'm at time. But I want to give a tour of like the next couple pages because there's some extra credit. Why is the angle addition formula true? And the answer is just like geometry. If you stare at this picture in the unit circle long enough and use the distance formula, you'll just be handed the angle addition formula. Alternately, there's like a mysterious looking triangle diagram right there. If you fill it in appropriately, you'll also be handed the angle addition formula. So pick which one of those two you like. There's some like neat geometry of complex arithmetic. You can use angle addition to get you to that. Cool.